All right, so let's start chapter 23. So by the way, so here there is a mistake. This is chapter 23, geometric optics classwork problem. Okay. All right, so the first one is the reflection related problem. So what we are given here, so we have two flat mirrors. Okay, so this one and this one. Okay, and the incoming ray, so this is the incoming ray make 15-degree angle with the first mirror. Okay, now the question is, what angle will the outgoing beam make with the second mirror? So that we have to determine. Okay, so to do that, we can just use the law of reflection. Okay, so the law of reflection tells us that the incident angle is equal to the reflected angle. Okay, so let's say this is the normal for the first mirror, then this is the incident angle. Okay, so you know that this is 90-degree minus 15-degree. Okay, and that is equal to 75-degree, right? So as the incident angle is 75-degree, the outgoing angle, I mean the reflected angle, will also be 75-degree. So this will be the reflected ray and this angle will be 75-degree. Okay, now let me use another color for the second mirror. Okay, now for the second mirror, this ray is the incident ray. Okay, and this is the normal for the second ray. Okay, and this will be the incident angle. So we have to know what is this angle. Okay, so you see that this is 75-degree and this is 90-degree, right? Because this is two normal, right, intersect here. So two normal intersect here means this is 90-degree. Okay, so then this angle will be 180-degree. So 180-degree, why? Because the three angle of a triangle is 180-degree. Okay, so the when you add the three angle of a triangle, it is 180-degree. So we know one angle is 90-degree, so I subtract 90-degree, and another angle is 75-degree. Okay, so this tells us that the incident angle here is 15-degree. Okay, so because the incident angle is 15-degree, the reflected ray should make an angle 15-degree with the normal. Okay, so that means this angle, okay, this angle is 90-degree minus 15-degree, which is 75-degree. Okay, and the question is, what angle will the outgoing beam make with the second mirror? So the outgoing ray is this one, and this makes 75-degree with the second mirror. Okay, so this is the answer. Okay, so you see that we just draw the some rays, okay, and law of reflection, and we determine the all right, so the answer for this one is 75-degree. Okay, so see that how I solve this problem. Okay, so try to understand. So here we just use the law of reflection and some geometry. All right, the second one. All right, so it is a mirror related problem. So we are given the concave mirror. Okay, and the radius of the concave mirror is 30 centimeter. Okay, so what we are given here is the radius of the curvature for a concave mirror. Okay, also the object distance is given. So it says that a 1.5 centimeter high object is placed 20 centimeter from a concave mirror. Okay, so this is the object distance and this is the object height. So we have to determine the position of the image and its size. Okay, so the equation, first equation we need is this one, F equal to R over 2, right? So the focal length is half of the radius of curvature. So that means 30 divided by 2 centimeter, and this is 15 centimeter. And because this is a concave mirror, okay, the sign for F will be positive. So we should use a positive sign for concave mirror. Okay, all right. Object DO is 20 centimeter. Okay, and normally object is positive. Okay, and object height is also positive. Okay, centimeter. Okay, so here you don't need to convert centimeter to meter, but even if you do it, you should get the correct answer. So I'm not, because all the numbers are given in centimeter, I'm not converting anything to meter. Okay, so the result will be in centimeter. Okay, now the first one, I want to know what is the position of the image. To determine it, we have to use this equation, the mirror equation. Okay, so this is the mirror equation. And if I solve it for di, I get something like this, 1 over f minus 1 over d0. Okay, so you can plug the value for f and d0. So 1 over 15 centimeter and 1 over 20 centimeter. Okay, and if I do this math, okay, I got something like this, 0.0167 centimeter inverse. Okay, now you see that what we derive here, what we calculated here is 1 over di, and I want to know what is di, not 1 over di. So what we have to do, we have to make it inverse. Okay, so what it means we have to do something like this. Okay, and that gives me 60 centimeter. Okay, and we get a positive sign here. Okay, so getting positive sign means the image is real image. Okay, so the image is real because the sign is positive. Okay, in this case both the object and image both are in the same side. Okay, that's why it is positive. Okay, now remember that for real image, the image is inverted. So we are going to check whether image is inverted or not. Inverted means we should get the image size negative. Okay, now let's do it. Okay, so we have to check that whether image is inverted or not. Okay, so how to calculate it? First, we use this equation, m equal to minus di do. Okay, and then we will be using m equal to hi ho. Okay, I think we don't need to do, I mean, we can do, we can combine these two equations together and get the image height. Okay, so we have to calculate hi. So hi is minus di do time ho. Okay, here di is 60 centimeter. Okay, do is 20 centimeter and ho is 1.5 centimeter, right? So this gives me minus 4.5 centimeter. So you see that we have a negative sign, and negative sign tells us that this is inverted image. Okay. All right. So this is for concave mirror. The next one is also for concave mirror. Okay. So let's do it. So concave means the focal length is positive. Okay. So what we are given in this case, we are given that concave mirror has the radius of curvature 30 centimeter. Okay, so here we are given the radius of curvature. That's why we have to get the focal length, we have to divide it by 2. Okay, because this is r by 2. Okay, and r is positive here because it is a concave. Okay, but remember that sometime you may just given the focal length. Okay, so when you are given just the focal length, you don't need to divide it by 2. Okay, so make sure you understand this. So here we are given the radius of curvature, that's why we have to divide it by 2 to get the focal length. Okay, but if you are directly given the focal length, then you have to just use that focal length. Okay, yeah, make sure you understand also the positive and negative sign. Positive sign for concave mirror, negative sign for convex mirror. Okay, so here this is the focal length. Object distance is also given. So object distance is plus 10 centimeter. Okay, and HO in this case is again plus 1 centimeter. Okay, so we have to determine the position and the magnification. So we have to calculate M and the position DI. Okay, all right. So again, the equation is 1 over DI plus 1 over DO equal to 1 over F. Okay, so we have to calculate 1 over DI. I mean DI basically. So let's first solve it for 1 over DI. Okay, and this gives us 1 over 15 centimeter minus 1 over 10 centimeter, and this term gives us negative 0.033 inverse centimeter. Okay, so you see that this is 1 over DI. Okay, so make sure you just don't keep this, you invert it. Okay, so we have to calculate DI, not 1 over DI. Many students forget to do the next step. Okay, so DI is 1 over whatever we calculated in the last line. Okay, and if you do the inverse operation, you get negative 30 centimeter. Okay, so here you see that you get a negative sign for the image distance, and that tells us that image is on the other side of the mirror. Okay, that means image is virtual. Okay, and virtual image is always upright. Okay, so this time we will see that the magnification is positive. Okay, so magnification here we just need to calculate the magnification, not the image size. Okay, so the magnification will be DI DO. So DI is negative 30 and DO is 10, positive 10. So you see that this and this cancel out, this negative and this negative cancel out, and M is just 3. Okay, so the magnification here is just the 3, and you see that you get a positive sign. Okay, and this positive tells us that the magnification or the image is upright. Okay, all right, so the next question is about the convex mirror. Okay, all right, so the last two problem we did for concave mirror, and the next one is the convex. Okay, and remember that for convex mirror the focal length is negative. Okay, and again we are given the radius of curvature. Okay, Yeah, let me tell you that in some question we are given the focal length, not the radius of curvature. Okay, so when we are given the radius of curvature, we have to divide it by 2, get the focal length. But if we have already given the focal length, don't divide it by 2. Okay, make sure you understand this. So here the focal length f will be again r by 2, but then r is negative. Okay, 16 centimeter. Okay, over 2. So it is negative 8 centimeter. Okay, all right. Focal length is given, and then it said that uh, the object is 10 meter. So here you see the object distance is given in meter. Okay, so do is 10 meter. Okay, so now we have to be careful. One is in centimeter, one is in meter, so we have to convert both either in meter or both in centimeter. Okay, so let me um oh, sorry. Yeah, I'm sorry. So it is meter. Okay. Sorry, this is 16 meter. Okay. All right. Yeah. So 16 meters. So yeah, we are fine here. So because it is given in meter, okay, we are fine. All are in meter. So our answer will be in meter. Okay. So what we have to calculate? We have to calculate the location of the image and its magnification, similar to the last problem. Okay. So again, we have to use the mirror equation. Okay, so mirror equation, if we solve the mirror equation for 1 over di, it will be something like this, right? It's basically this equation. Okay, so here f is 1 over negative 8 meter, and do is okay, do is 10 meter. Okay, and if I do this math, it should give me something like this, minus 0.225 inverse meter. Okay, and then di will be 1 over negative 0.225 inverse meter, and that is equal to negative 4.44 meter. Okay, and negative sign tells us that the image is on the other side of the mirror. Okay, that means it is virtual. Okay, and yeah, it makes sense, because if you remember from the lecture that the convex mirror make only virtual image. Okay, so virtual image means the image distance is negative. Okay, so that makes sense. But for the concave mirror, we can have both virtual and real image, and we see those in the last two problem. And virtual image is always upright, so we'll see that magnification is positive. Okay, so the magnification is minus di do. Okay, so 4.44 meter for di, and do is 10. So this negative cancel out. So what we get is 0.444, and it is positive. Okay, and this positive tells us that the image is upright. Okay. Okay. All right. Next. Okay, so this is a refraction problem. Okay. So here you see that we have a glass, we have air, we have air. So this is the glass, and you see this light refract through the glass. So here this is the refracted ray. Okay, and this is also the refracted ray. So this refraction is from air to glass, and this refraction is from glass to air. Okay, all right, and we are given that this angle is 60 degree. Okay, and the index of refraction for air is 1, for glass it is 1.5. Okay, this is 1. So these numbers are the index of refraction of the medium. Okay, now if so, we have to calculate what is the angle of refraction in the glass and what is the angle of refraction. Okay, what is the angle at which the ray emerges from the glass. Okay, so we have to calculate two things. First one is what is this angle, what is theta A. Okay, and then what is theta B. Okay, all right, so these two things we have to calculate. And again we have to use the index law of reflection and law of refraction here. Okay, all right, so first let me calculate what is theta A. Okay, so you see that, I mean, let's first focus on this refraction. Okay, air to glass. Okay, so this is theta, this is in angle of incidence, and this is angle of refraction. Okay, now if you remember, the law is n1 sine theta 1 equal to n2 sine theta 2. Okay, so we know theta 1 is 60 degree and theta 2 is theta A, which I want to know. Okay, so let me solve it for sine theta 2. So sine theta 2 is equal to n1 divided by n2 sine theta 1. So n1 is 1, n2 is 1.5 sine 60 degree. Okay, and the right hand side, if you do the calculation, you should get something like this, 0.577. Okay, so theta 2 or theta A here, okay, is basically the same thing, is sine inverse 0.577, and that gives me 35.2 degree. Okay, so what we learned here, the angle of refraction from air to glass is 35.2 degree. Okay, all right, now we know that theta A is 35.2 degree. Okay, so after refraction it will it follow this line. Okay, okay, now we want to also know what is this refraction angle. Okay, so that means after, so there will be another refraction here at this point between the glass and air. So this one was between air and glass, and this one, the next one, will be between glass and air. Okay, so in this case it is going from glass to air. Earlier it was from air to glass. Okay, now in this case you see that this is a parallel line, this is a parallel line, and this line, this refracted ray in the glass, connect these two parallel line. Okay, now from the geometry you can show that this angle and this angle are the same. Okay, so this is the geometrical rule. Okay, so now we know that this angle is 35.2 degree. Okay, we have to calculate what is this. Okay, now we are going to use the same law of refraction. Okay, so n1 sine theta 1 equal to n2 sine theta 2. Okay, now you know that n1 n2, I mean, we have to change. So now our n1 is the glass and n2 is the air. Earlier it was opposite. Okay, so n1 is 1.5 here, sine theta 1 is sine 35.2 degree, n2 is 1, and sine theta 2 we have to calculate. Okay, now if I solve it for sine theta 2, it gives me 1.50 sine 35.2 degree. And if I calculate, it gives me something like this, 0.866. And similarly, we can calculate theta 2 by using this. Okay. And this time we get 60 degree, exactly 60 degree. So this time theta 2 means theta B is equal to 60 degree. Okay. All right. So here you see that we just use law of refraction or the Snell's law and some geometry. Okay. So you know that this chapter is about geometric optics. So you have to use some geometry. Okay. All right. The next few problems are about lens. Okay. And remember that in lens, we are going to use the same equations that we use for mirror. Okay, although the sign convention is little bit different. Okay, that you have to remember. All right, the first one, we have to calculate the position and the size of the image. Okay, of a this centimeter high leaf. So this is HO. Okay, placed 1 meter from, so 1 meter means this is DO, and from a plus 50 millimeter focal length camera lens. Okay, so here it's already explicitly mentioned that this is plus, so F, this is F equal to plus 50 millimeter. Okay, so that means this is the converging lens, converging or convex lens. Okay, for convex lens, okay, it is positive, focal length is positive, which is opposite of the mirror. Okay, for concave mirror, focal length is positive. Okay, remember that. Okay, so beside this, so you see that one is given in centimeter, one is given in meter, and one is given in millimeter. So it's better to convert everything in meter. Okay, so let's do it. So here we are going to determine what over di. Okay, and the equation is very similar to mirror. So let me write down just the final equation, right? So if you solve the mirror lens equation, in this case we call it lens equation, we get 1 over di equal to this, and 1 over f is 50 times 10 to the power minus 3, because it is millimeter, so I convert it into meter, and do is given 1 meter, so we don't need to convert it. Okay, and now if you do this math in your calculator, you should get something like this, 19 inverse meter. Okay, so then di will be 1 over 19 inverse meter, and that is equal to 0.05266 meter. Okay, so this is the image distance, and here you see this is positive. Okay, and positive means we get real image. Okay, and for lens, real image means the image is on the other side of the lens. Okay, and this positive also tells us that real image is, sorry, yeah, so real image is always inverted. So we will see that when we calculate the magnification or the size of the image, you will see that it is negative. Okay, so we will see that. Okay, so to calculate the image height, okay, image size, let's use these equations. Okay, so these are the two equations you already know. So you have to calculate basically hi. So hi, if I solve this equation for hi, I get something like this. Okay, and here di is 0.0526 meter, do is 1 meter. Okay, and ho is 7.60 centimeter. So you can keep it in centimeter or you can convert it into meter. Okay, so if you do this math, you should get something like this. Okay, so minus 0.0526. Okay, so this meter cancel out. So here actually we don't need to convert it into centimeter if I want to keep it in centimeter. But yeah, you are free to do that. Either keep in centimeter or meter. Okay, so let me keep just in centimeter because the image, the object height is given in centimeter. Let me calculate the image height in centimeter. So actually you don't need to convert. Okay, just keep 7.60 meter. Okay, so if you do this math, you get something like this. No, 0.400 centimeter. And here you see that you get a negative sign, and negative means inverted. So you get inverted image, and it makes sense because real image should be inverted. Okay, all right, next one. Okay, so this is image object distance. So an object is placed 10 centimeter from a focal length converging lens. Converging lens means f equal to positive 15. Okay, and we have to calculate similarly the image position and size. Okay, all right, so very similar to the last problem, we can write di equal to 1 over f minus 1 over d0. So 1 over f here is 15 centimeter and 1 over d0 is 10 centimeter. Okay, so if you do this math, you should get something like this. Okay, so here, because all the numbers are given in centimeter, so you don't need to worry about it. You can keep all in centimeter. So di should be 1 over that number. Okay, and so di is negative 30 centimeter. Okay, and negative means the image is virtual. Okay, and in this case image will be in the same side of the lens. Okay, so yeah, you know that for lens it is different than mirror, so don't confuse between the mirror and lens. And virtual image is always upright, so we will see that the magnification or the size of the image is positive. Okay, now we are going to do that. So m is HIHO minus DIDO. So HI is similar to the last problem, is this one. And here di is negative 30, do is positive 10, ho is, oh, ho is not given. Okay, so ho, so this and this cancel out, and what we get, plus 3 times of ho. So the image will be 3 times larger than the object. So image will be 3 times larger than the object. Okay, and this positive sign tells us that image is upright. Okay, all right, the next one. So now it is a diverging lens. Okay, so for diverging lens, the focal length, remember that it should be negative. So f is negative 25 centimeter. Okay, okay, so where must a small insect be placed? So here this tells us that where the object should be placed. if the lens is this one, the focal length of the lens is this one, and the image is formed, virtual image is formed 20 centimeter from the lens. Okay, so remember that here we are some information given virtual image. Remember that for virtual image, di is negative. So here you know that we are not given the sign, explicit sign, but you have to remember from the virtual image that the image distance will be negative in this case. Okay, so yeah, and also it says that on the same side of the object. So for the lens, if the image and object are in the same side, then the image is virtual. Okay, so here in this case we have to calculate d0. Okay, so the lens equation is this, right? So now we have to solve it for do. So 1 over do is equal to 1 over f minus 1 over di. So 1 over f is negative 25 centimeter, and then 1 over di is 20 centimeter. So if you do this math, so it will be something like this: negative 1 over 25 plus this negative and this negative cancel out. So here we will have a positive sign, so 20. And then if you do this math, you get 0.01 centimeter inverse centimeter. Okay, so then because it is 1 over d0, you just need d0. So d0 is 1 over 0.01 centimeter inverse. Okay, and the calculator tell you that this is equal to 100 centimeter or 1 meter. Okay, so the object should be placed 100 centimeter from the lens. Okay, all right. Okay, so here we have the combination of lens. Okay, so both are converging lens. So the focal length for this one is positive, this one is also positive. So this and this are the okay, so this is B. Okay, and this is 80 centimeter. Okay, and the object for the first lens is object distance is 60 centimeter. Okay, we have to calculate the position and the magnification of the final image formed by the combination of the two lens. Okay, so if we have something like this, we have to solve the image distance separately and the magnification separately for both lenses and then combine. Okay, so let's see how to do that. So first let's solve for A, okay, lens A, and then we'll be doing this same thing for lens B. Okay, so di, so we have to basically calculate the di. Okay, so I'm just writing di because we are using this equation several times. Okay, so for the first lens, the focal length is 20 centimeter and do is 60 centimeter. Okay, and do is normally positive, so I'm just using the positive sign. And if you do this math, you should get 0.033 centimeter inverse, and then di is 1 over 0.033 centimeter inverse, which is equal to 30 centimeter. Okay, and here you see that you get a positive sign. So for the first lens, you get real image. Okay, but inverted. Okay, a real but inverted image. So let's say the object was somewhere here. This is 60 centimeter. Okay, and then after refraction, the image produced somewhere here. Okay, 30 centimeter. I mean 30 centimeter. Okay, now let's say this is the image. Okay, so image should be inverted because it is real image, right? Although, I mean, also you can calculate M. Okay, so M1 or MA will be negative DI DO. So it is 30 centimeter divided by 60 centimeter. Okay, so you see that it is negative 0.5. So negative means it is inverted. So for the first lens, it should be inverted. Okay, now this so this is the object for the second lens. Okay, so because this is 30 centimeter from the first lens, and the distance between the two lenses are 80 centimeter, I mean is 80 centimeter. Okay, then this distance is 80 minus 30, so it should be 50 centimeter. Okay, so the object distance for the second lens is 50 centimeter. Okay, now we have to calculate what is the image distance from the second lens. Okay, so B, so same equation, 1 over di equal to 1 over f minus 1 over d0. Okay, so this is 25. Okay, so the focal length for the second length is 25 centimeter, and then this is 50 centimeter. The object is 50 centimeter from the second lens. So if you do this math, you should get something like this, 0.020 centimeter inverse. So for the second lens, di, the image distance is this. Okay, and this is basically 50 centimeter. Okay, and this tells us that image will produce somewhere here at 50 centimeter from the second lens. Okay, and so we get 50 centimeter positive sign, and this tells us that image will be again real image. Okay, and inverted. Okay, inverted with respect to the object. Okay, so that means because this is inverted, one more inverted means this is something like this. So this is inverted with respect to this. Okay, so the image will be something like this. Okay, somewhere and something like this. Okay, and you can see that mi is m is equal to minus di do. So here di is 50 centimeter. Okay, and do is also 50 centimeter. Both are positive, so we get negative 1. Okay, and then the total m is ma and mb, the product of ma and mb. Okay, so the total magnification is the product. So ma was negative half and mb is negative 1. So you see that you get a positive sign, positive 0.5. So image, the final image will be the half time the object. Okay, and this is positive, and this is positive means it is upright with respect to the original object. Okay, so although you see that this is inverted with respect to this one, but this and this are upright. Okay, and the positive sign tells us that the final image will be upright. Okay, that's it. Does that I mean this double convex lens. Okay, now we have the same thing. Okay, here we have one convex lens and one concave lens. Okay, so this time you will see that it is little bit complicated than the last one. Okay, but once you know once you understand how to solve the mirror, I mean the lens equation, it is not that difficult. Okay, so here we have two lenses, one converging lens, one diverging lens, and you remember that Converging lens means the focal length is positive. Diverging lens means the focal length is negative. Okay. Okay. So here we have to calculate the focal length of the diverging lens. So we have to calculate what is the focal length for the second lens, and what we are given. We are given that, okay, so 28 centimeter. So it says that when parallel ray strike the first lens, we get the I mean they converge at this distance. Okay, they converge at this distance, 28.5 centimeter. Okay, and it says that if the converging lens has a focal length of 16 centimeter, what is the focal length of the diverging lens? Okay, all right, all right. So okay, so let me read it again. Okay, so it would be probably easy. So we have the parallel rays. Parallel rays strikes on this lens. Okay, after refraction, um, they um, they merge somewhere here. Okay, and this tells us that the focal length of this combination is 28.5 centimeter. Okay, and there are different way to solve this. Okay, I'm just going to solve similarly what I use in the last problem. Okay, so that means I use two different mirror equation, one for the converging lens, one for the first lens, one for the second lens. Okay, so for the first lens, let me first calculate 1 over di. So 1 over di will be 1 over f minus 1 over do. And it says that the parallel ray from the sun. Okay, so parallel ray from the sun means do is equal to infinity. So 1 over d0 is 0. So 1 over di is basically approximately equal to 1 over f. Okay, so di basically equal to the focal length. Okay, and what it is 16 centimeter. Okay, so after refraction from the first converging lens, okay, the I mean uh, they meet here. Okay, so the image for the first lens formed somewhere here. So image of the sun, for example. Okay, now this is the object for the second lens. Okay, so object for the second lens. Now you see that it should be the object should be on this side, right? But in this case, the object is on the other side. Okay, so that's why we have to be careful here for the second lens. Okay, so for the second lens, let me write down the equation. So 1 over di plus 1 over do equal to 1 over f. So here we are going to calculate f. And what we are given? We are given 1 over di. Okay, so 1 over di in this case. Okay, so let me let me talk di later. First, let me talk about do. So here do is basically 16 centimeter. Okay, but because it is on the other side, so it's supposed to be in this side, but it happened on the other side. Okay, so in this case the object distance should be negative. Okay, so object supposed to be on the left side, but somehow because of this combination it is on the other side of the diverging lens, so we have to use a negative sign. Okay, and for di is on the other side. Okay, so normally when di is on the other side, okay, it should be positive. Okay, so the image from the second lens is produced here. Okay, and it tells us that this distance is 28.5 centimeter. So the image distance here is 28.5 centimeter. Okay, And if I solve this equation, you will get we will get f. Okay, so what I get here is this, and that is equal to negative 0.0274. Okay, and if I invert it, I get minus 36.5 centimeter. Okay, so the focal length for this one is minus 36.5 centimeter, and it makes sense because you see that we get negative sign, and negative sign is for diverging lens. Okay, so for diverging lens, focal length should be negative, and we get negative sign, and that makes sense. Okay, so the focal length of the diverging lens is negative 36.5 centimeter. All right, so that's it for this chapter.